Welcome you all to organometallic reagents. In this module, already we had two lectures. In the first lecture, we studied Grignard reagents. The second lecture, we focused on organolithium reagents. In this lecture, we will cover organocopper, organozinc, and oxymercuration demercuration reactions. Here, the preparation of organocopper reagent is shown. When you react with alkyl or aryl lithium and copper iodide, you can try to generate organocopper complex, which can further undergo reaction with organolithium to give the Gilman reagent. Professor Gilman also is known as father of organometallic chemistry. This is an example shown here. Methyl lithium undergoes reaction with the copper and iodide in diethyl ether to give this methyl copper complex, which undergoes further reaction with methyl lithium to give the dimethyl organocuprate reagent, and this exists in dimer in diethyl ether solvent. And in place of methyl group, you can also have other alkyl group like primary, secondary, tertiary alkyl groups, alkenyl and aryl. They can readily undergo reaction with the copper and iodide to give this the corresponding organocopper complex, which can be further reacted with another equivalent of organolithium reagent to give this the respective Gilman reagent. This is also known as lower order cuprate. Now, let us look at the reactivity of the Gilman reagent. If you look at the alpha beta unsaturated carbonyl compound, you can see there are two electrophilic center . This hard electrophile and this soft electrophile, when you react, if you remember in the case of organomagnesium compounds or organolithium compounds, they readily undergo reaction with this carbonyl group. 1 to addition, we used to get the corresponding addition product. However, here in this case, when you use the Gilman reagent, the reaction takes place at the beta carbon, because this is just I mentioned soft electrophile. And if you compare the nucleophilicity of the Gilman reagent, so this is soft nucleophile. So, this soft nucleophile undergoes reaction at the soft electrophile. Therefore, 1,4 addition is favored in the case of Gilman reagent. And if you have the nucleophile, it undergoes addition, and you will be able to get the corresponding 1,4 addition product. This is in the case of Grignard reagent, the 1,2 addition is favored, and you will be getting the corresponding alcohol as the product. This is quite different from the this is a difference between the Gilman reagent and organolithium, organomagnesium reagents. And in case of just organomagnesium, for example, is given here. When you react with methyl magnesium bromide or methyl lithium, they readily undergo reaction with the carbonyl group, the carbon of the carbonyl group. And on the other hand, when you use this this cuprate reagent, and which undergoes reaction at beta carbon, and you get the corresponding addition product. Therefore, in the case of cuprate reagent, and like ester, amides, they do not react. This is, but whereas in case of Grignard reagent or organolithium, they readily undergo reaction. These are the difference between this Gilman reagent and organomagnesium or organolithium reagents. So, now let us look at the application part. Here some examples are shown which involve conjugate addition reaction. If you look at the first example, here we use this dimethyl cuprate, which undergoes reaction, 1,4 addition reaction, to give this compound in 55% yield. As we have seen just now, it can undergo addition. So, you will be able to generate this copper 3 intermediate, which can give the product by reductive elimination. So, when you do the workup, so you will be able to get the corresponding ketone as a product. This is how the reaction takes place. So, the next example involves the higher order cuprate. This is known as higher order cuprate. Cuprate reagent. So, just I have mentioned this is lower order cuprate. So, the difference between this shows slightly higher reactivity. It shows higher order reactivity comparing to the lower order cuprate. This can be easily prepared if you have in this case 2 equivalent of lithium reacts with copper cyanide, copper 1 cyanide, and generates this So, now the cyanide is not bonded with the copper, therefore, it is written like this, it is bonded with the lithium. So, this shows higher reactivity comparing to the lower order cuprate. Another example here, again reaction of this cuprate shown with this alpha beta unsaturated ketone, and so after the reaction you will have this enolate, and which in situ undergoes a nucleophilic substitution. This is a good leaving group, nucleophilic substitution to give this bicyclic ketone as the product. So, these are the basic and examples. These reactions have been well explored now. The asymmetric versions of these reactions also have been considerably done. For your understanding, I have taken 3 examples, simple examples, where we can see the first example as the ester group, and it is intact under these conditions. So, you can try to selectively react with this alpha beta unsaturated double bond here, and through 1,4 addition you can get the addition compound. So, this is different from the Grignard reaction, where this ester also can undergo reaction, but under these conditions, since methyl is less nucleophilic nature, selectively it undergoes the 1,4 addition, you can get the addition product. The last example we have seen, you can also following the conjugate addition reaction, you can also try to do nucleophilic substitution with the enolate. In this way you can try to generate the bicyclic system with the excellent stereochemistry. So, mechanism of this conjugate addition reaction shown here. Addition of this can give this intermediate. This is a copper 3 intermediate, this is a copper 1. Once if we have this one, then this can produce, it can give this enolate through reductive elimination. Once you form this one, when you do the workup, you will be able to protonate, which can isomerize to the ketone. This is how the reaction takes place. Here 1,4 addition followed by you get this copper 3 intermediate. Once you form this one, this can undergo reductive elimination to give this product. So, in this reaction, if you look at it, you generate one equivalent of this copper complex as a byproduct. So, here reaction of acid chloride into ketones are shown here. You can also try to react Gilman reagent with acid chloride to give the ketone. Vinyl cuprate has been shown with this cyclohexyl chloride. The reaction of this vinyl cuprate reagent has been shown with this acid chloride to give the ketone as the product. And similarly, here the reaction of this acid chloride, which also has ester as a functional group, can be reacted with this dimethyl cuprate to give this ketone as the product. So, these are very important transformations, because you cannot make these compounds using this organomagnesium or organolithium reagent, and you can make this vinyl ketone as a product from acid chloride. And similarly, here you can also try to convert this acid chloride into ketone, where you have the ester group present in the molecule. The next example is the reaction with epoxides. You can also carry out the opening of the epoxide in this case. So, this reaction takes place less from less sterically hindered side, and stereospecifically you can open this and you get this alcohol as a product. And similarly, in this case you can open of this, you get this compound. You can do here, it goes via SN2 pathway. Reaction takes place via nucleophilic substitution, and the Gilman reagent approaches from the less sterically hindered side, and you will be able to form the corresponding alcohol as the product. Here the substitution reactions are shown. This depends upon the mechanism of this reaction. Mostly there are two possibilities. It can go via nucleophilic substitution SN2 pathway. Alternatively, you can also undergo oxidative addition followed by reductive elimination. Depends upon the nature of the substrates. A reaction of this vinyl bromide with organocuprate has been shown here, and this coupling can be carried out in a good yield. Similarly, here this reaction of this dibromo derivative with this dimethyl cuprate is shown here, which can be reacted to give this geminal dimethyl derivative in good yield. Similarly, this also this organocuprate can be reacted. This tosyl is a very good leaving group via SN2 pathway. You will be able to form this long chain alkyl molecule in good yield. So far we have seen three type of reactions. First one, we have seen the conjugate addition reaction. Then we have seen the opening of epoxides, then reaction with acid chloride, and you can also carry out the coupling of, if you have the vinyl or alkyl halides or alkyl tosylate, you can try to couple with organocuprates in good yields. In addition to that, you can also carry out reaction with allylic acetates. Some examples are shown. In this case, if you look at it here, and you can react so this can undergo reaction, and you will be able to get this compound. If you look at here, whatever the organocuprate approaches the opposite side of this acetate group, and you will get with the excellent stereochemistry. And here another example, this one involves a vinyl methyl substituted cyclohexyl acetate. Here if you look at, this is equatorial, this also equatorial, and 1 to equatorial trans. when you react this with this dimethyl cuprate, so you will be able to get this compound as a single isomer in good yield. On the other hand, if you take this axial and equatorial on this cis, so in this case, and they exist in the equilibrium, and this they undergo reaction with this organocuprate reagent to give a mixture of alkenes. If you look at it here, you get here E and Z mixture, you get a mixture of geometrical isomers. When you take this trans one, equatorial, it undergoes reaction So, in this case the reaction selectively takes place and you get this geometrical isomer as a single compound. On the other hand, if you take this methylvinyl cyclohexyl acetate, which they exist as shown here, they ready both undergo reaction, you end up with mixture of geometrical isomers. So far we have seen some of the reactions which can be carried out using organocuprates, and mostly we have seen the use of lower order organocuprates, in other words Gilman reagent, and you can carry out addition 1,4 addition reaction, you can carry out substitution reaction, you can also try to open epoxides, you can try to react with acid chlorides. At the end we also have seen, and you can also, if you have allylic acetate, you can try to react, you will be able to get the addition product. So, that depends upon the substrate, and we have seen 2 examples where you can based on the nature of substrate you will be able to get the corresponding alkene as a product. The next, let us go for the Glaser coupling, and if you have alkyne, terminal alkyne, and you can try to react, you can try to couple, you can dimerize in the presence of copper aluminum chloride and base under oxygen, where oxygen acts as a oxidant. And for example, if you take this phenylacetylene, 2 molecules of phenylacetylene can combine together, you will be able to get this homocoupled 1,3-diene as a product in the presence of copper aluminum chloride, ammonium hydroxide in the ethanol solvent. This deprotonation of this acidic proton using base can, and followed by reaction with the copper aluminum chloride, can generate this intermediate. You will have so once you form this one, the presence of oxygen, it forms a radical. These 2 radical can combine together and you will be able to get the dimerized compound as a product. So, you can see the application of this reaction is very important transformation. For example, you can try to make the cyclic polyalkyne derivative using this reaction. When you take this alkyne derivative in the presence of copper chloride, DMEDA in dichloromethane at 0 degree Celsius under oxygen atmosphere, you can try to trimerize to get this macrocyclic molecule in 47% yield. So, just we have seen, if you have the phenylacetylene and copper aluminum chloride in the presence of base and oxygen, you can dimerize. On the other hand, you can also heterocouple. For example, you take phenylacetylene, you can also take another acetylene having halogen here, and once if you have this one, now you can try to couple them using copper aluminum iodide in the presence of base under reflux conditions, and you can use different alkyne here. First the base can deprotonate the acidic proton which can undergo reaction with the copper iodide, then you will be able to generate pyridinium, the salt. So, you will have this complex. Once you have this one which can undergo oxidative addition with this iodide derivative, one oxidative additive can give this copper intermediate which can give this product by reductive elimination. You regenerate the copper iodide. So, catalytic amount of copper iodide is sufficient, you can carry out this reaction, you can do heterocoupling of two alkyne derivatives under these conditions. Now, let us look at an application of this reaction. For example, here the coupling of this alkyne with this vinyl iodide is shown here in the presence of copper iodide and potassium carbonate under heating. As we have seen just now, deprotonation of this acidic proton by base can followed by reaction with copper iodide can first generate this copper acetylene derivative. Once you form this one, then now which can undergo oxidative addition intramolecularly with this vinyl iodide, then you will be able to generate this intermediate copper 3 intermediate. This can give the product by reductive elimination, and you will be able to get this macrocyclic lactone as the product. Now, another example, this is the intramolecular reaction. This example involves intermolecular coupling of this terminal alkyne with this iodobenzene derivative. This can be coupled using copper 1 oxide in the presence of pyridine under heating, and you will be able to generate this compound. In this case, this alkyne first can react in the presence of base, and you will generate this intermediate. Once you generate this one which can undergo reaction with this iodobenzene derivative, then you will be able to generate so this can give the product by reductive elimination. So, once you form this one in this case, and you have the so you will have this product. Once you form this one, under these conditions it undergoes intramolecular cyclization. See, it undergoes intramolecular cyclization to give. So, copper can here also can make chelation. So, once you form this one, you get the cyclic compound as the product. So, here what happens that coupling followed by cyclization happens, therefore, you will end up with this benzofuran as the product. So far we have seen the reaction of organocopper reagents. Now, let us move to the reactions of organozinc reagents. There are several methods are available to prepare organozinc reagents. Here some of the examples shown. If you have the aryl halide, for example, here iodobenzene derivative which can be reacted with the zinc metal, by insertion you can get this, you start with the zinc 0 oxidative addition, you can get this organozinc reagent. Similarly, if you have you can also if you have alkene, you can react with the boron. So, you will be able to have in this case so which can, when you react with dimethyl zinc by transmetallation, you will be able to generate this organozinc reagent which can be used for carbon-carbon bond formation. Similarly, you can also in the presence of this titanium catalyst, you can try to react with zinc iodide and lithium hydride, you can form this compound. This the regiochemistry depends upon the alkynes. So, there are several methods are available. In this way, you can try to make the organozinc reagents. Now, let us see some of the important and common applications of the organozinc reagents. One of the popular reaction is the reformers reaction, all of you know very well. When you have the alba bromo ester, so you can try to react with the zinc which can undergo addition with ketone to give this beta hydroxy ester as a product. This is very important transformation. So, the mechanism of this reaction shown. So, alba bromo ester can undergo reaction with the zinc, you will form this enolate. Once you form this one, this enolate now can undergo addition reaction with the ketone and you will be able to generate so this cyclic intermediate. Once if you have this one, this can now undergo reaction as through this cyclic transition state to give this enolate. When you do the workup and you will be able to generate this beta hydroxy ester as a product. Here some of the examples shown where you can find the use of reformers reaction. Here the reaction of this allyl bromide is shown with this aldehyde in the presence of zinc powder and iodine, and you can try to react with this aldehyde and you will be able to generate this lactone. You have the once after the reaction you will have the OH group which can undergo intramolecular reaction to give this lactone as a product. Now, another example here, the reaction of this alba bromo ester with in the presence of zinc is given. It can undergo addition followed by desulfurization can give this pyrrolidine derivative as the product. So, the other interesting example is the Simmons-Smith cyclopropanation which involved zinc carbonide reagent and when you take the zinc and react with the diiodomethane, and you will be able to form a organozinc intermediate which can now undergo reaction with alkene. Stereospecifically you will be able to get the cyclopropane derivative. For example, if you take cis alkene and you can try to react with the zinc and diiodomethane, and you will be able to form this reagent. Once you form this one which can transfer intramolecularly this methylene, you will be able to form the cyclopropane derivative. On the other hand, if you take the trans one, and similar way you can make this trans cyclopropane. This reaction has also been well explored, and so many now you can also carry out the asymmetric version of this reaction. Here some examples shown, and you can, for example, in this case you have the two double bond, and this can make chelation with this were so chelation, then this the bottom phase of the alkene, the cyclopropanation takes place, and similarly here the chelation of this reagent that leads to the formation of the cyclopropane in the top phase. So, this when you have the chelating group and the reagent can make chelation, you can try to transfer the methylene or the top or bottom side, depends upon the stereochemistry of the chelating group. Another example given here, you can also try to do cyclopropanation by in this case, and you will be able to get the top side. As you have the ketone which can make chelation, you can introduce, make the convert the double bond into cyclopropane with the excellent stereochemistry. The other interesting reaction is the cross coupling reaction, and whenever you have the aryl iodide and you can try to couple with organozinc reagent using palladium based catalyst, you will be able to make the biaryl system. One example shown here, in this case here, this lithium reagent can couple with this bromo derivatives, 2-bromopyridine derivatives in the presence of palladium catalyst and zinc chloride via cross coupling reaction, which has been used to construct this medicinally important heterocyclic compound. So, Professor Nigeshik got Nobel Prize for his contribution in this cross coupling reaction using organozinc with aryl halides using palladium catalyst. This reaction has wide applications in carbon-carbon bond formation reactions. The mechanism of this reaction shown here, oxidative addition of this palladium 0 complex can give this intermediate. Once you form this one, which can undergo trans reaction with this organozinc reagent through transmetallation, and you will be able to generate this palladium 2 intermediate, which can now give the product by reductive elimination, which can undergo cis trans isomerization, and followed by reductive elimination can give the product where you generate the palladium 0, which can undergo further reaction with the halo substrate to give the oxidative addition, which can further react with the organozinc reagent to give the product through reductive elimination. So, the next part of we are going to see is the reaction of organomercury compounds, oxymercuration, demercuration. This is also very important reaction. If you have alkene, if you want to transform into alcohol, and it has wide applications. And in this case, if you, for example, when you react this alkene with the mercury acetate and followed by reduction, and you will be able to form the introduced OH group at more substituted carbon. This is what happens here, and let us look at this one. This alkene, the OH group is introduced here, and similarly in this alkene, allylic alcohol, you can also try to react with mercury acetate in the presence of methanol. Now, instead of here OH group, here water is a nucleophile here, you can also use methanol, and in this way you can make the methoxy ether as the product. In this case, you get mixture of compounds, and the mechanism of this reaction shown here, and this alkene can react with the mercury acetate, and you will form this mercurium ion intermediate. Once you form this one, and now This carbon is more electrophilic nature, like carbocation, like this one now, which can undergo reaction with this nucleophile. Opening up this one, you will be able to generate this intermediate. Once we have this, can lose proton, and you will be able to have this hydroxy derivative, which can be now converted into alcohol by using the sodium borohydride reduction through demercuration reaction. The stereoselectivity of this reaction shown here, and so if you have chiral center next to the alkene, you can try to generate diastereoselectivity. In this case, the anti-diastereomer is major compound, so you can try to produce a 3:1 ratio. This can be understood from this Newman projection, whatever shown here, and this is the favored one, and this is the disfavored one due to steric reason, and this conformation is favored. Therefore, you get this anti-diastereomer as the major product. In summary, we have seen today the reaction of lithium organocuprate, and we have seen the preparation of organocuprate and the reaction with for several reactions, and mostly the organocuprates are used for the conjugate addition reactions. In addition to that, you can also try to use for reaction of allylic acetates, substitution reactions, opening of epoxides, reaction with acid chloride, where you can try to generate ketone as a product. Then we have seen the Glaser coupling, which involves the dimerization of alkynes in the presence of copper 1 halide and base and oxygen, where we acts as an oxidant in this reaction. You can dimerize the alkyne, you can get the homocoupled product. You can also try to couple two different alkynes through Castro-Stevens coupling, and one of the alkynes should have the terminal CH bond, which can be deprotonated using base. It can be reacted with the copper 1 halide. You will have the copper acetylene complex, which can be reacted with another alkyne having the halogen, and you can undergo oxidative addition. You will have the copper 3 intermediate, which can give the product by reduct elimination. Next, we have seen the reaction of organozinc reagent, and there are several methods are available to prepare organozinc, and we have seen few examples. If you have the halogen, you can also aryl or alkyl halide, you can try to react directly with the metal. Oxidative addition, you can make the organozinc reagent. Alternatively, you can also make through transmetallation. We have seen one example. You can react with the boron reagent, then you can react with the dialkyl zinc. In this way, you can try to make organozinc reagent. Alternatively, you can also, if you have alkyne, you can use a titanium catalyst. You can try to add organozinc reagent. In this way, you can make new organozinc reagent for the reactions. Then we have seen some applications how you can use for the some of the reactions we have seen. One is a repharmacy reaction, and we have seen the application of repharmacy reaction for the to make macrocyclic system, inter and intramolecular reactions. Then we have seen also the Nikesh-Kress coupling reactions. If you have the organozinc, alkyl or aryl halide, you can try to couple, and in this way you can make new class of compounds. And at the end of the lecture, we have seen the reactions of organomercury compounds. We have seen some examples of the reactions of alkenes to alcohols and other reactions to ethers via oxymercuration, demercuration using mercury acetate, and in the presence of appropriate nucleophile, you can try to convert alkene to the addition product. With this, we conclude this lecture. Thank you very much.